Good afternoon. Welcome back. So it's Thursday and we're talking about algebra. We're going to pick up where we left off last time, which was we were talking about grouping, but overall we're talking about factoring. Okay. The first thing I want us to remember is that factoring sometimes looks to be the opposite of simplifying. Okay. I want to highlight this idea here because, again, to look forward to where we're going, when we were talking about simplifying, we did addition, we did subtraction, we did some multiplication. We haven't talked too much about division. And so what I want us to recognize is that factoring is going to be a big tool in simplifying division or fraction problems. So in general now, we're going to be talking about factoring polynomials, and today talking about factoring quadratics. But it's going to look like sometimes we're kind of making things more complicated than they were already, right? The quadratic we're looking at, for example, our first example here, x squared minus 4x minus 45. That is a simplified parabola, quadratic. There's no multiplication or division to be done. There are no parentheses. The terms can slide commutatively. For example, we could write this like this. We can move things around, right? So it's simplified, but it is not factored. That'll be useful for simplifying. It'll also be useful for telling us things about this function. For example, really common thing we want to know about functions, when are they equal to 0, right? What x can we put in there and have 0 come out? Well, factoring will help us figure that out because we are undoing a distribution, or we are creating a situation where distribution could be used. And so what we're looking at here, I'm actually going to do this one first in the style that I would do it myself. We're going to talk through how I get that. But first I want to show you what factoring is, right? So I've established this equal sign. I'm going to say that I'm going to prove that it's equal by distributing this out. So x times x is x squared. X times 5 is plus 5x. Negative 9 times x is negative 9x. Negative 9 times 5 is negative 45. We get to simplify this. We say the 5x and the minus 9x combine. We verified our equal signs, right? And in particular, we verified the first one by actually doing the distribution. So you can see these equal signs, they're bidirectional, right? We can go either way. So we could factor or we could distribute. We could factor or we could distribute. That's equal. They're equivalent expressions. And we can go back and forth if we'd like, right? Now, on this line, I could factor, and it would be x minus 9 times x plus 5. But look at the two forms, right? This is a simplified form, right? Same as this one, because there's no distribution to do, because there are no sets of parentheses, because the terms can move. It's a general form of a polynomial. There's only one term of each degree. We've even organized it left to right, high degree terms to low degree terms. But this factored form tells us some information, because when we plug x in to either the general form x squared minus 4x minus 45 or the factored form x minus 9 times x plus 5, we will get the same result, right? Plug in, for example, 5. 5 squared is 25, minus 20 is 5, minus 45 is negative 40. plug in 5 to the bottom, negative 4 times 10, negative 40. So we can plug things in and they give us the same thing. That's the virtue of being an equivalent expression. That's what it means. But in this secondary form, we can find out when what x's give us 0 out very, very quickly, because we need to remember, this is something to really pay attention to and commit to memory. When we're factoring, one of the reasons we do it is because 0 times anything is always 0, or 0 multiplied by anything is always 0. So you can look at this. Let's just look at this term. When is it 0? Well, when x is 9. And when x is 9, the second term is 14, but 14 times 0 is 0. We don't actually care that 9 plus 5 is 14 in this case, because whatever that second parentheses wound up being, the first term is 0, so multiply it by whatever and you get 0. Similarly, if we looked at this second term in isolation, when x is negative 5, that's going to make that term 0. 0 times whatever is 0. So this is a value to factoring, and we'll get to solving problems of that case, but I just want to give you a look ahead of like why we're doing something like this, why factor in the first place. There are a couple of reasons. One of them is solving for zeros. One of them is simplifying rational functions. So let's just do a couple examples and let's get used to what we're looking at here. So x squared minus 5x minus 6. Let's factor that. So factoring means we're trying to come up with an equivalent expression, which is the multiplication of two expressions that involve parentheses, usually. So, okay, first thing I'm looking at here, I want the x terms in each to multiply together, and I need two of them, right? Because x times x will give me x squared, and this term has an x squared. So I establish for myself this so that I can be assured to when I multiply this out, regardless of what happens in the blanks in these two, x times x in the distribution gives me the x squared that I need. Now you can kind of see in this initial question here, what happens in the distribution? We get two x terms, right? Now what is unique about those two x terms? Well, they need to add to this, right? So we're looking for two numbers that add to -5 in this case. There are a bunch of options, but there's another constraint to it, which is coming from this piece. They need to also multiply to that. So how can I get two numbers that multiply to -6 but add to -5? Those must be -6 and +1. We can verify. Let's actually do the distribution. Well, x times x is x squared. X times 1 is plus x. -6 times x is -6x. -6 times 1 is -6. Simplify. X squared minus 5x minus 6. Check. What I want to say here is that today we're going to look at only examples where we have just one x squared. Next week, on Tuesday, we'll look at examples where we have maybe a different coefficient to the x squared term. So we're trying to factor this into a distribution question. We know that we must have 1x squared. We know that we must have negative 17x's after the distribution. So maybe it's negative 16 and negative 1. Maybe it's negative 13 and negative 4. Maybe it's 20 and negative 20 and positive 3. But they also have to multiply to 72. So we think about our factors of 72 for a second. 72 and 1, 36 times 2. What else do we have? 18 times 4. 6 times 12. Also 8 times 9. And what I'm noticing is 6 times 12 is going to give me an 18. 8 times 9 will give me 17. I like that. And then I'm establishing them both as minus because they need to add to negative 17 and multiply to positive 72. Let's verify. X times x is x squared. X times negative 9 is negative 9x. Negative 8 times x is negative 8x. Negative 8 times negative 9 is plus 72. It's looking good. Simplify as usual. Note that after this, we've factored. That is factoring. All that I'm doing beyond that is just verifying. It's not necessary. It is a good idea, especially as you're learning and strengthening your factoring skills. Verify that you've done it right. And it just reiterates for everyone like what we're actually doing. We're writing an equivalent expression. These equal signs verify that the factored form is in fact equivalent to the top form. All right, let me do a little erasing. Okay. So factor x squared plus x minus 42. So we need two numbers that add to 1x and multiply to negative 42. Well, let's think factors of 42 here. 1 and 42, 2 and 21, 3 and 14. 4 won't have a factor, isn't a factor. 5, no. 6, yeah, 6 and 7. 6 and 7. That's useful, because immediately as I'm saying 6 and 7, I notice that they are one number apart. That's very useful to adding 2x, if one is positive and one is negative. How do I pick which one? Well, it's a positive x. So I need the 7 to be positive. Let's double check. Looking good. So this is the factored form of this. Remember, factored form, one of the things that lets us do is say, hey, when x is negative 7, apparently this will be 0. When x is positive 6, likewise. You can verify that if you'd like. Let x be negative 7. The first term is 49. Minus 7 minus 42, that's 0. Let x be 6. First term is 36. Plus 6, 42 minus 42, also 0. Now, as a quick aside, I mentioned that let's compare this to this. right? This has changed in the 2, and so this changes in the factoring because we need them to distribute and get to the right term. Factor that. Nine times 7 is 63. As those will combine to 2, positive 2x. Let's factor that. Now, note the difference. There is no x term in this one compared to the prior ones. But recall, 0, x, we don't write. So it's useful to remember that this is in fact equal to this. So it starts to look similar. Now this has a special name. It's called the difference between two squares. We notice that 36 is the square of 6. So it does in fact factor. Like that. Notice those are inverses of each other and add to 0. Interestingly, not everything factors. So for example, I should say is not everything factors to whole number factors. So this, for example, it is not, although you might want to say it is not equal to this. Oh, it's the sum of two squares. I'll just do the same thing, but with both of them being pluses. Why? Well, do the distribution here. It's x squared plus 6x plus 6x plus 36. That's x squared plus 12x plus 36. That is not equal to this, right? So that is an incorrect factoring. And for the record, this has no whole number factoring. In fact, it has no factoring at all because it has no times that it is 0. There is an idea that you may have come across of imaginary numbers. The letter I stands for the imaginary number square root of -1. That's appropriate here, not necessary to know, but it's useful to think about if you've come across that idea. But in general, when we're factoring in the real numbers, we have nothing to do with x squared plus 36. That is fully factored. So now I want to write at the same time a series that we could look at here, a series of factoring questions. So just so we can compare for a second. Oops. Let's do x squared plus 7x minus 8. Let's look at x squared plus 3x plus 2. Let's look at x squared minus 49. How about x squared minus 2x minus 35? Trying to think of one more. Okay, so 5 examples of quadratics, polynomials, all whole number coefficients. In this case, all degree 2 polynomials, and all with the leading coefficient or the coefficient to the x squared are all 1. It's implied, but recall, if we haven't written a coefficient, it's 1. If we haven't written a term, the coefficient is 0, like we saw and like we see here in this x squared minus 49. So I'm actually going to erase them again to get back here. So what I want to do is highlight some of the differences, right? So for example, plus x terms, minus x terms, and no x terms, minus coefficients, plus coefficients, right? The x to the 0 term. But each might be able to factor. So it's not the combination of pluses and minuses that determine entirely whether it can factor. There's more criteria to it. What we're looking at here then is ways to get to multiplying to the final number, the last number, and adding to the middle number. So this factoring business, when it comes to quadratics, this is the first style. Remember that when we do learn new concepts in math, a typical approach is to layer on complexity, right? Complications to the situation. In this case, one of the complications that isn't there is that initial fact that I point out that the coefficients to all these x squared terms is 1. Okay, that's making things easy for us, a little bit easier, because we know those two terms are x and x. If it's going to factor at all, right? It has to be that way. I highly, highly suggest doing a lot of these and just becoming very, very familiar with what you're doing. Remember, in each case, we are undoing a distribution. We are writing an equivalent form with a distribution. You notice that all my factorings are two lines multiplied together. Now I want to recall then that we can go back and forth between factored and unfactored, or factored and general form of quadratics. So let's start now. What if we were looking at something like this, but we changed it a little bit and maybe put a 2 out here? Then what is the original form that we're factoring from? Well, 2 times x squared So what are we seeing then? This is an example to illustrate something that could change. From the examples that we've just been doing to this one, what are some of the differences? Well, I think it's fairly noticeable that this 2, actually I don't want to highlight that one. This 2 is different than the previous ones. And we can see there now where it shows in the original 2x squared plus 8x minus 42. What we see, if we go this direction upwards from the bottom to the third equivalent expression, we're actually in kind of one of our initial from last week situations of factoring, where we can say, oh, they all have a 2 in common. All these terms have a 2 in common. So this factors to this. They're all even. Interestingly, this 2x squared plus 8x also factors like this. Oops. Mixed up my signs. Now, what do we see different here compared to our original example and compared to some of the examples we've done today? Well, 14 and -3, they do multiply together to -42, but they don't add together to 8. You notice that? We've been thinking in the original examples like, oh, okay, we need 2 numbers that multiply together to the last number and add together to the middle number. They don't do that here, but I'm claiming that the factoring is actually correct. What is happening here? Well, this term, the 2 here, is more influential than we might first anticipate in the factoring. It's very influential here. So -3 times 14 is -42. -3 times 2 plus 14 is +8. What are we talking about here? Well, let's do the distribution out. 2x squared minus 6x plus 14x minus 42. Notice these these middle terms, the ones that need to add to 8. We're not talking about 3 and 14. We're talking about 6 and 14, specifically -6 and 14. So that 2 is influential. And we can notice then that this line, we can pull out the 2 from the first term. So there may be different paths to factoring, but we're going to get the same result. Factoring is a major skill for algebra. It's something that you want to do enough of so that you understand the process, but also the purpose. And we've talked a little bit about process and a little bit about purpose today. One of the purposes is going to be simplifying rational functions, or functions where we're dividing 2 polynomials. Another purpose is finding the x values which create the times when the polynomial is 0 as an output. We can see from this factored form, for example, that'll happen at x equal +3 and x equal -7. So factoring is a big idea. We'll probably do it all through next week and even into the following week as we're tying it into different ideas like factoring cubics or simplifying rational functions. So I look forward to seeing you then. Until